This is topic 6.3, the first fundamental theorem of calculus. And in this topic, we're actually going to be working backwards from what we're used to. Instead of taking the derivative, moving forward, we could think of going backwards and finding the antiderivative. So let's take a look. The derivative of velocity is acceleration. Let's go ahead and take that derivative. 2t minus 6. So the derivative of that velocity function is 2t minus 6. Now, what if I wanted to go backwards and see what s of t was? Okay, so what would I take the derivative of and get t squared? Well, it would be 1/3 t cubed. Now, you might wonder where I got that, but let me show you over here. If I start with t squared, I'm going to add 1 to 2 and divide by that. So that when I take the derivative, 1/3 times 3 is 1, t, take 1 away. So when we take the derivative of a function, we multiply, and subtract 1. When we integrate, we add 1 and we divide. Okay, so let's go ahead and see if we can do that for this next term. Minus 6t, if I add 1 to that power, right now it's a 1. If I add 1 to that, that's a 2. Take negative 6 divided by 2, that's a negative 3t squared. So if you take the derivative of negative 3t squared, you're going to get a negative 6t. So we added 1 and divided. Now how about that 2? What did you take the derivative of and get 2? You guessed it, 2t. But now I have a question for you. Can't there be any constant at the end of this function? Absolutely, because the derivative of a constant is 0. So we're going to call this our constant of integration. So it is a must, and points are always taken off if it's not included. Okay, so let's practice. Remember, we are adding 1 and then dividing, going backwards. Actually, what they call the inverse operation of finding a derivative. So let's also work on our notation. They gave us f prime of x. So now we are going to write f of x. So add 1 to this 3 and you get a 4. 4 times 2 is 8. So 8x, I hope I didn't just mess you up. So add 1 to 3 and that's 4, and then divide 2 by 4. Okay, add 1 to that x to the first, it's 2, and divide that by 2. And then what do we take the derivative of and get 7? 7x plus any constant. So I just want to simplify that. 1/2 x to the 4th minus 5/2 x squared plus 7x plus c. Now what makes these nice? You can actually go and take the derivative of your antiderivative and see if you got it correct. So the derivative here would be 4 times multiply, 4 over 2, 2x cubed, that's what we had. Take that 2 over here, minus 5x to the first. Derivative of 7x is 7. So it should be pretty straightforward and quite fun. Okay, I'll switch colors just so I don't jumble up. F of x, they gave us f prime. Add 1 to 4, and it's a 5, so 1/5 x to the 5th. Minus, add 1 to 3, it's a 4, so 3 over 4 x to the 4th. plus 5 over 3x cubed minus, now be careful here, this minus x is a negative x to the first power, okay? Remember, we're going to add 1 to that 1, so it's a 2, and divide, so it's a negative 1/2 x squared. And you can convince yourself of that. If you take the derivative of this, you'll get a negative x. And then you guessed it, plus x squared plus 5x plus my constant of integration. I don't need to put a square around that because that's so big. Okay, just like when we were taking the derivative in the past, we want to write our functions so that it's easier to use our power rule, so to speak. So this is x to the 1/2 minus 4. Let's go ahead and find f of x. So I'm going to take 1/2 and add 1. So that would be 3/2. And then I have to divide. So that's 2/3 x to the 3/2 minus 4x plus c. Okay? So sometimes little notes like this help you. So add 1 and divide. So I think that's kind of cool because now we have our basic rule for integration. And it looks like this. The integral of x to the n is equal to add 1 and divide x to the n plus 1 all plus c. Okay? So it's not too difficult, but that might be something that you want to practice or convince yourself of with that formula. Okay? Okay, so now let's take a look and look at an indefinite integral. Now, when we integrate, we're going to actually call this f of x, and we use a capital F of x. And you're going to see this quite often. And really what they're saying is that if you take the derivative of this function, you will actually get f of x. To me, some of this can be quite confusing. And and of course, we want to put plus c there. But sometimes that can be a little tough. So let's go ahead and do some practicing and see what we get. Okay? So we went ahead and found antiderivatives there, and now we're going to go ahead and use some interesting notation. So we are finding the antiderivative. We are working backwards. But the notation is not necessarily needed because we were given f prime of x and we would give them f of x. Okay? Now we just learned that the integral is the antiderivative of that function that we are integrating. We can't forget that constant of integration. Okay? So let's go ahead and do this. What do we take the derivative of and get 9? You guessed it, 9x. Now we'll write our minus sign. You might find it easier to leave a space and add 1 and then divide. And some students have said that that helps them. Plus c. And again, you could take the derivative of this and make sure you get 9 minus x squared, and you'd be able to check it. Now, let's go ahead and write this in nicer notation. 6x to the negative 2 minus x to the negative 3 dx. And here we go. I'm going to add 1 to negative 2, and that's a negative 1. Be careful. And now I'm going to divide by a negative 1. Okay? Minus, I'm going to add 1 to a negative 3, and that's a negative 2. And now I'm going to divide by a negative 2, which makes that a plus. Okay? And then I can't forget about my constant of integration. Now technically, if the original function was not written with negative exponents, technically you have to leave your answer without negative exponents. So you may see solutions like this: a negative 6 over x plus 1 over 2x squared plus a constant. Okay? Look at this next integral. This is important because we need to simplify this, and I always say share the denominator. Each one of those terms in the numerator we will divide by x, and now we will integrate. So let's add 1, which would give us a cube, and then divide by 3, minus add 1 and divide 4 by 2, and we get 2. The antiderivative of 7 is 7x plus c. Okay, so I now introduce the first fundamental theorem of calculus. This is also known as FTOC1. Okay? And basically it goes like this. If a function f is continuous on the closed interval ab, and f, there's that capital F again, f is the antiderivative of f of x on that interval, then the integral from a to b of f of x dx is going to be f of b minus f of a. Remember, f of x is the antiderivative, and I'm going to show you how to do this. But basically, you'll be plugging in these limits of integration, and b goes in first, the upper goes in first, into the antiderivative, okay? Don't let that bother you. Maybe I should take this off right there, and that looks better, okay? Personally, how I like this written is I like it to say this is equal to the antiderivative evaluated from a to b. Now I'll take that upper limit of integration and plug it in first, and then subtract. Look how important that minus is. Subtract, and then go ahead and plug a into it. Let's give it a whirl. Evaluate this definite integral. So what we'll do is we will first write the antiderivative. So I'm going to add 1 to x, and it's a 3, and divide by 3, and that's just a 1. Plus, the antiderivative of x is 1/2 x squared. That is worth memorizing. Minus 2x. Now watch what's going to happen. Evaluate from 2 to 6. There is no constant of integration with definite integrals because there's no formula. We are definitely integrating. We want the area between 2 and 6 here, so there's no reason. Now, this is interesting. Now we're going to plug 6 into this function. So everywhere there's an x, we're going to put a 6. 6 cubed plus 1/2 times 6 squared minus 2 times 6. But wait, that's not all. Now we're going to subtract, very important, plugging in a 2. So 2 cubed plus 1/2 times 2 squared minus 2 times 2. Okay? So this is the antiderivative evaluated at 6 and the antiderivative evaluated at 2. So that's really, really important. Okay? So if you work that out, I believe you would get 216, but guess what? You can check this 216 by using Math 9. And I'll leave that to you. Okay? Now, let's go ahead and try this next one. Definite integral from -2 to 5. So we first write the antiderivative 4x minus, I'm going to add 1 to that exponent, which is now a 2, and take 6 and divide it by 2, and I get 3. We're going to evaluate that from -2 to 5. So now remember, I'm plugging that 5 in first. And let's go ahead. 4 times 5 minus 3 times 5 squared. All of that is the antiderivative evaluated at 5 minus 4 times -2 minus 3 times -2 squared. All of that is the antiderivative evaluated at -2. And if you work this out, I believe you get a -35. Yes. And you can check that using Math 9. Okay. Now, let's go ahead and look at this next problem. Evaluate the definite integral from 0 to 3. So I think this is worth going ahead and graphing. So what does the absolute value of x minus 2? I don't know if you know this, but the actual line y equals x minus 2 is a line that intersects the y-axis at -2, and it has slope of 1. I'm just going to bring this all the way down like that, okay? Now, when you take the absolute value of a function, anything below the x-axis gets flipped up, gets reciprocated or reflected across the y-axis. So actually, this is what our graph is. I really just wanted to show you that, just in case you weren't aware of that. So now let's go ahead and find that area between 0 and 3, and let me switch highlighters so you don't get confused with that green line. So 0 and 3. So now you can go ahead and just use geometry and see if you can find that, or what you could do is you could go ahead and split these up into 2. Now geometry won't work for everything, and this one of course it would. So I want to make sure that you understand that if you are finding the area under an absolute value curve like this, you can't just plug it into x minus 2, okay? So what if we said that this was equal to, and so taking this part right here, what if we said it was equal to the opposite of the integral from 0 to 2 of x minus 2 dx first? Because basically, if we took the area here, it would be negative. And so if we want that, we could just take the opposite of it. So that works out fine. And then we'll go ahead and take the regular derivative, the integral from 2 to 3 of x minus 2 dx. So just the regular area there, okay? So then let's go ahead and write our antiderivatives. Now, of course, you can flip that back and then plug the other one in first if you want to do that. That doesn't hurt. So we can now just take the integral from 2 to 0 of x minus 2 dx plus the integral from 2 to 3 of x minus 2 dx. Our antiderivative is 1/2 x squared minus 2x evaluated from 2 to 0 minus that same antiderivative evaluated from 2 to 3. Okay? So I have a little bit more work to do. I'm going to come around here, and if I plug 0 into this function, I'm going to get 0. But now I have to subtract plugging in a 2. And if I plug in a 2 there, I'll switch pen colors. It's 1/2 times 2 squared minus 2 times 2. So that's 2 minus 4, that's a negative 2. So this would be a negative 2. Now that's just this first part. Now I have to do the same thing again. Minus, and now I'm going to plug a 3 into that. And if I plug a 3 into this, I have a 1/2 3 squared minus 2 times 3. So that's 9/2 minus 6. And this is a nice margin to write in. 9/2 minus 6 is going to be a negative 3/2. Okay? So be careful with your parentheses. You definitely have to have parentheses here. A minus 3/2. And now we're going to subtract, plugging in a 2. So we have 1/2 times 2 squared. Actually, we've already done that. 1/2 times 2 squared minus 2 times 2. And that's 2 minus 4. That's a negative 2. So now I'm going to change this to a positive 2. So if you add this up, it looks like we have a 2 plus 3/2 minus 2. And it looks like we'll end up with 3/2. Now I'll leave that to you to double check. You can go ahead and math 9 that. Maybe that's 2 plus a half. I have to go back and look at that. Let's see. I'll leave that for you to check. Did I forget that? Positive 2 plus 3/2 minus 2. And 1, 2.5. I think that answer should be 2.5. So I can go back and check that. I do believe that that's 2.5. So you know what I might do? Not a problem. Okay, I'm just going to say that this is equal to 2.5. Okay, and you can just check that, plugging the 0 in and then the 2, and then plugging the 3 in and then the 2. And I think what might have happened is this negative sign here. You have to subtract all of this. And this fundamental theorem of calculus uses a subtraction as well. Okay, find the area under the curve for the integral, for the interval from 0 to 2. Okay? So let's go ahead and take a look and see what they want. We could split this up into two different, I think I have, yeah, there we go, a little dotted area here where I can go ahead and show you that I'm going to split that right there. We have two different curves. So that total area under that curve is going to be equal to, so the area under from 0 to 2 is going to be the integral from 0 to 1 of x squared dx, plus, now we're on the other side, the integral from 1 to 2 of 2 minus x dx. Keep in mind, we can always add areas. So now we have 1/3 x cubed evaluated from 0 to 1 plus 2x minus 1/2 x squared evaluated from 1 to 2. Now, if you plug in 1, you get 1/3, and subtract plugging in a 0. That was nice and easy. No mistakes made there. Plugging in a 2, that's a 4 minus 2, and that leaves us with a 2 minus, plugging in a 1, I get a 2 minus a half. And 2 minus a half is 3/2. So that would be 1/3 plus, minus, there you go, you see, you have to keep track of me, 2 plus 4/2 minus 3/2 is a positive half. and you'll end up with 2/6 plus 3/6, and that's 5/6. And you could just say 5/6 units if you'd like. Okay, set up this integral, but do not evaluate it, okay? So how would we set that up? What would we say? Well, we're going to go ahead and to find the area of the shaded region. This is not an integral. So when we find the area, we actually want the integral. If we integrated this area right here, we would get a negative. So when we want the area, we want to always make it positive. So if you integrated from 0 to 2 here, of course it's going to be positive. But if you integrated from 2 to 3, it's going to be negative. That integral is going to be negative. Why? Because that's areas under the curve. But we need total area. And so we will have to take that integral when we integrate from 2 to 3 and take the opposite of it to make that area positive. Okay? So let's go ahead and do this. This total area is equal to the integral from 0 to 2 of the opposite of x minus 1 squared plus 1. Kind of an ugly function, but that's what it is, okay? That's positive area. This will give us a positive value when we integrate that because the area is under the curve. But now what we want to do is we want to take the opposite of the integral from 2 to 3. So we are going to add the opposite of the integral from 2 to 3 of x minus 3 squared minus 1 dx. And the reason why we did this is now going to also be a positive value because the integral would be negative. So let me take these off and we'll simplify this. Okay, and that's equal to the integral from 0 to 2 of the opposite of x minus 1 squared plus 1. Whoops. And you could just say minus the integral from 2 to 3 of x minus 3 squared minus 1 dx. Now, let me tell you that you could also take the absolute value of that second graph. So 0 to 2 of the opposite of x minus 1 squared plus 1 dx plus the integral from 2 to 3 of the absolute value of x minus 3 squared minus 1 dx. And that's saying I want total area. Okay? X minus 3 squared minus 1. Okay? So either way, that will give that to you. Okay? And now you can start your practice. That concludes this first part